So I'm going to let you read through those properties for definite integrals. It seemed like most people were reading through them in class anyway. They're pretty straightforward, and they mostly work how you would expect them to work, given what we know about rules for derivatives so far, and just algebra rules that you're used to. The one I want to say just a little bit more about is this additivity rule. Notice here, I have the integral from a to b of f plus the integral from b to c of f. It's these two limits. You can kind of think of them as the inside limits. This top limit and this lower limit here, they're the same. It's kind of like they cancel each other out. It's like you're going to glue the two pieces together at b. You're going to stop one piece at b, pick up the next piece starting at b. So it's like you can smush this into one integral, which is why we have the integral from a to c. And that's what this picture here is, to kind of help you understand visually. The one thing that you might not notice is that it's not actually even required that b is between a and c. I could have written the integral from a to c plus, let me try that one more time. I could have written the integral from a to c of f of x plus the integral from, as long as this upper limit matches c to b of f of x dx. And I can think of those c's canceling. That's going to equal the integral from a to b of f of x dx. And if that feels weird, just notice that we already know the integral from c to b is the same as the opposite of the integral from b to c. So this says the integral from a to c, so the whole plus the opposite of this. So the whole minus this part is equal to the integral from a to b. So just the takeaway here is, as long as these two limits match, it doesn't matter it doesn't matter that c is between a and b. This property still holds. So we had a lot of people working on this in class already, but to review here, I'm going to use the properties to try to simplify some of these expressions for definite integrals. So these are things I know. It doesn't say how I know them, but I've been told them. If I want to find the integral now from 4 to 1 of f of x, I'm going to use that changing the order of the limits rule, because I know the integral from 1 to 4 of f of x. So I'm going to write that the integral from 4 to 1 of f of x is equal to the opposite of the integral from 1 to 4 of f of x dx. And that's equal to the opposite of, I can replace this integral, the integral from 1 to 4 of f of x dx, with -2. So my final answer, +2. The second one, I want to find the integral from -1 to 4 of f of x. Notice that there's no way this can help me, because that tells me about the area under h. B is all about the area under f. But I notice that to cover the whole distance from -1 to 4, I could break that up into the area under the curve between -1 and 1, and the area under the curve between 1 and 4. So that's what I'm going to do. I choose to write this out as equal to, actually I choose to write this. I'm going to write this out here. This integral is equal to the integral from -1 to 1 of f of x dx plus the integral from 1 to 4 of f of x dx. And I double check. That top limit and that bottom limit are the same, so I could write this as one integral from -1 to 4, which is what I'm trying to do. So this is equal to The integral from negative 1 to 1 of f of x is 5, plus the integral from 1 to 4 is negative 2. So final answer, 3. This next one, the integral from negative 1 to 1 of 2f of x plus 3h of x. So I'm going to start by splitting this up at the addition sign to an integral that has a sum in the integrand. The integrand just means the stuff that's inside the integral. I can rewrite as the sum of two integrals. So this is not this problem. This is me rewriting this one. That's equal to the integral from negative 1 to 1 of 2f of x dx plus the integral from negative 1 to 1, 3h of x dx. I split this up. I make two separate integrals, splitting it up here. Notice this dx belongs to both 2f of x and 3h of x, which is why it shows up in each of these integrals. Now each one of these integrals happens to have a constant multiplier in there, so I can use the constant multiplier rule. This is going to be 2 times the integral from negative 1 to 1 of f of x dx, plus 3 times the integral from negative 1 to 1 of h of x dx. And that's going to be 2 times, well, this integral is equal to 5. And this integral is equal to 7. So it's going to equal 10 plus 21, 31. Final answer. That's an equal sign. Okay, so we were talking about this in class with some of you at least. When we get to letter D, I'm asked to find the area between 0 and 1 under the F curve. Well, I know the area under the F curve between negative 1 and 1. But I don't have any other information about F between 0 and 1. So without any other information, this is just here to help you avoid that error of thinking if you have half of the distance, you can just cut the area in half. We don't know that because we have no guarantee that this function f is at all symmetrical. So here we have not enough info to answer. That's not enough info. Same idea with letter E. I know something about the area under H between negative 1 and 1. But just because I extend the interval out one space in either direction, I don't know anything about H's behavior to the left of negative 1 or to the right of positive 1. Except, yeah, I don't even know anything about H. I knew something about F. So again, I have not enough info to simplify this expression. Now later, if somebody tells me the h of x function, we're going to get into the next section and we're going to know exactly how to find that definite integral using calculus. But right now, if we're using geometry and using properties, like the properties that are listed on that front page, just not enough information. Okay, we're about to have a pretty exciting moment. You've seen a lot of functions in your time as a mathematician. Sometimes the function will tell us sometimes the function would tell us that we should take our input and square it. Sometimes the input ends up being the exponent. Sometimes the input gets used inside a trigonometric function. Now that you have had an introduction to the definite integral, we're going to use function notation in a new way. We're going to make a new kind of function that you've never had a chance to see before. It's pretty cool. Check it out. There we go. So I'm going to write a new kind of function where the variable, the input, becomes the upper limit on a definite integral. So I'm going to start practicing this function. This function is going to come up a lot in the next couple of chapters. So here's just a very basic introduction to it. We're just going to practice using this function and replacing that upper limit to make a definite integral that we're going to simplify using these properties we've just been practicing. So g of 1, I just want to write this expression so I get a little bit used to it. If this is g of x is the integral from 1 to x of f of t dt, then let me write g of 1. That means I'm going to look at this function rule, and anywhere I see x, I'm going to replace it with 1. This will be the integral from 1 to 1 of f of t dt. Notice that a common error would be to replace any variable that you find with 1. Some people erroneously write, oh, I'm going to plug in 1. That means I'm going to replace this with 1. But that's not what this notation means. F is, or in this case, g is a function of x. So when I give you an input, that's what you're going to replace the x's with. You don't get to replace anything else. Well, so this means that g of 1 is the area under the f curve between 1 and 1. So our job now is to simplify this expression. And we know that whenever the lower and upper limits of an integral match, there's an area of 0. You could imagine, here's 1. When the input to the f function is 1, I can find the height of that rectangle. But the distance between my two endpoints is 0, so the rectangle is going to have no width. This is going to be an area of 0. So now I'm going to try this. I'm going to compute g of 4. Start by labeling an expression for g of 4. So g of 4 is going to be the integral from 1 to 4 of f of t dt. And now I'm going to come to my picture. I'm going to try sketching in, or at least identifying that area. It says find the area between 1 and 4. Here's 1. Here's 1 and 4. And I want to find that area. So it's going to take a little bit of geometry, but it's not a complicated idea. I need to find this area, which part of it is above the y-axis. I'm sorry, above the input axis. And some of it is below. I have this little triangle that hangs below. So now I'm going to have to do some geometry to figure out this area. And it's my job to keep track of my work, but that's all I got to do. So that's going to be, I'm going to split that up into a trapezoid and a triangle and a triangle. So this trapezoid has two heights that are different. So I'm going to take their averages, 3 plus 1 over 2. That's the average of the two heights, times the width of that trapezoid is 1. Plus, this is a little triangle here. It has a base of 1. Oh, triangle. So 1/2, base of 1, height of 1. And then down here, I've got this little triangle that hangs below the input axis. So I'm going to subtract that area. I'm going to happens to also have an area of 1/2, 1 times 1. So when I go to simplify this, I can see that this area and this area are opposites. They're going to cancel. So my final answer, 4 over 2 times 1 to make 2. So g of 4 equals 2. Okay, last one. I'm going to find g of -2. I'm just crossing that out so you know I'm really working on this one. So first I'm going to write an expression for g of -2. That's going to be the integral from 1 to negative 2 of f of t dt. That means I need to find the area under the f curve between 1 and negative 2. But that feels weird because those two limits are out of order. If I'm going to use areas, if I'm going to use geometry by looking at this picture and trying to find areas, I need my limits to go from smaller to bigger. So my first step is going to be to change the limits. But if I do that, I'm going to have to take the opposite of the integral. So it's going to be the opposite of the integral from negative 2 to 1 of f of t. Now I can look at my picture. Between negative 2 and 1, that's nice. It's one single triangle. It's above the input axis, so I just have to find the area of that triangle. But notice I still have a negative here. This is going to be negative. To clarify, that negative is this negative. And now I'm going to write an expression for this integral, which is going to be the area of that triangle. So it's going to be 1/2. The base is 1, 2, 3 spaces long. And the height is also 3. So that area, negative 9/2. And I'm going to put my label back on it. So that's g of negative 2 is negative 9/2. Final answer.